this is G everywhere, and I can have this Lie bracket before substitution. This is the Lie bracket. What is the rank of this guy? It's rank 2. Why? Because actually f is nothing but negative x times the Lie bracket. So this Lie bracket is, this guy is not new in comparison to this guy. At any point in the three-dimensional space, this is just a scalar multiple of this guy, right? It's just the x coordinate. So this is rank 2 everywhere. And can you tell me anything about delta? Look at it here. What can you tell me about delta? Take two vector fields f and g, the Lie bracket f and g is here. Take two vectors f, g, and g, the Lie bracket was what? 0. So it's here in the span. Between this guy and this guy, it's 0 in the span. So delta is what? Involutive. Very good. Delta is involutive. Okay. So delta is involutive, and what can you conclude now? Integrable by Frobenius. Very good. What do you mean by integrable? What do you mean by integrable? That there is a slice. We live on a slice, right? We can integrate. There exists some lambda function R3 to R such that what? I will do it the easy language. Nabla lambda dotted with all these vectors is 0, right? With G dotted with the Lie bracket f and g, right? So let's get this guy, for example. What is this? Nabla lambda dotted with g. Here is g. So this is just say the partial lambda partial x is 0. Okay, which means lambda is a function of y and z only. That's great. What about here? Let's do this dot product. So we have 0 and negative lambda y, negative y lambda z. This is 0, right? And we can solve this PDE. This will not provide any new information because this equation will be just x multiplying that equation, right? Because f is just x multiplying this vector field. So let's solve this equation, and we know how to solve it. dy divided by the coefficient equals dz divided by the coefficient, and I can integrate y dy is y squared over 2 equals z plus constant. So I have this guy here. This is x, this is y, this is z. I have a parabola in the yz plane, so here is my parabola, and it's constant along x, so it's extruded along x, like that. And so this is indeed your integral manifold, right? So if you start anywhere here, no matter what you do with your control, you will not leave that surface. It's a thin slice in your entire three-dimensional space. Whoever designed this control system should go to jail. I mean, this is very badly designed control system, right? Obviously, you need one more actuator. Any question about that? Any question? So don't rely on your intuition. Why? Because this seemed at the beginning that, there is no major problem, but when you compute things and you use our tools, you realize that it's not. And I will do it the other way around. Again, don't rely on your intuition, because here is a Bianchini and Stefani example. (1990). So we have x dot is u, y dot is x. We just showed that if this is the thing, the system is very badly designed. It's not even accessible. I mean, controllability is out of the question. So what about having here x cubed? Does it really change things? Okay, so if it was x times y, I know it's not even accessible. But x cubed y, well, really don't rely on your intuition, go and compute things. So I have f and g, right? So let's compute. So g of 0 is obvious here, 1, 0, 0. And when you do Lie bracket at the origin, so you get, this guy will give you -1 here. And if you keep doing that, you get this. Actually, this is, everything else vanishes until you get here. Add g3f at the origin. This is something like 0, 0, I guess 6 or something. Okay. I live in 3-dimensional space, and now I cover the tangent space x, y, and z, right? So the Lie infinity of f at the origin is R3, so I'm done. The lark is great, which means what? The lark implies what? Accessibility. Very good. What do you say about controllability? So first of all, it's not like the previous example where here x, y is not even accessible. Now it's accessible. Second, let's see. So what vector fields I'm using to cover the tangent space? I'm using G, which obviously I can reverse the flow along. If G the same, I can reverse the flow along. What about this guy? Let's count how many G's in there. Let's count how many G's. 1 and 3. So we have 4 G's, right? 4 G's and 2 F's. So it seems that there is a problem here, right? Actually, yeah, we gave it a name, I forgot to tell you. This is an obstruction to local controllability. Whenever you have even number of G's, this guy, where? This guy, this. So this is even number of G's, we call it an obstruction to local controllability. A potential obstruction. Okay? It can or cannot. So here it is really precluding controllability. Over there now it's an obstruction to local controllability. Does it really preclude controllability or not? We need to assess that. So in Sysman's theorem, one of the outcomes of Sysman's theorem 1987 is that brackets of the type, so we have here like f and g, okay? Even and even, these are actually good brackets. If they are the other way around, like the previous example, so this is odd and even. I mean, whenever we have even number of control, it's a problem, right? Because we're afraid that we cannot switch. They will not be able to switch sign or to change sign. It turns out if you have odd f, yeah, this problem persists. But if you have even f, this what they call this is not. It's not just my fancy name. It's the, you can say, the official word. It's good brackets, and these are bad brackets. Okay. Well, but how? How, when we have this guy, we can solve the problem? So I'm here in 3-dimensional space, x, y, and z. Okay. Where was the problem? So I have the 3 vectors that cover the tangent space: G, the Lie bracket, and this very large bracket that we're just saying it's a good bracket. Okay. This covers motion along the x. This covers motion along the y. And this guy that is skeptical, this covers the motion along z. Okay. So motion in the xy plane is fine, and the problem is with z. Okay. So we're saying we're accessible, but it seems we suspect that we are small time locally controlled. So here was Sysman's solution. Find u that steers the system from the origin to some 0, 0 and z final, with z final is non-zero, of course. Okay? Can we do that? Are we sure that we can reach that point? Are we sure that we can get, so from the origin, we're going to do some play around with controls, and finally we will reach some value along the z-axis, whether it's positive or negative. Are we sure about that? Why he is just stating it like, okay, get me this control and I'll tell you how to do the next. Why we're sure? This is the origin, and I want to reach point here or point there in some time t. Are you sure that you can find this control? Are you sure that we can do it actually? Of course, why? Because we're accessible. So, well, the motion along the xy is guaranteed. Any xy is guaranteed, in particular the origin, of course. And the issue is about z, but we're accessible. So in the z directional, my reachable set will look something like that. With x not seems to be on the boundary so far, but I can reach some positive value or the other way around. I have some issue, some directionality issue in z, right? So I can reach some positive values or negative values, but I don't think that we can reach both, okay? Any question about that? We're sure by accessibility, by the lark, we're sure that we can get here. And if we can get here, we're asking, okay, if I can achieve some positive z, can you achieve this negative z? Because if we can, then we're small time locally controllable, right? So he's providing you the solution. Then this control law will do it for you, which he called U inverse. It's the reverse of your control that you find. So it's actually applying your control in reverse, t minus t. So you got a control sequence, and you have it from 0, say, to 1 second. Then the very first reverse control to apply is the value at 1 second, and do it by reverse, okay? This control, or reverse control, will steer the origin to 0, 0, negative z5, okay? So you can apply this trick always, whenever we have this type of good brackets, okay? So,
so now we are controllable?
Yeah, the system is small time locally controllable by system theory. So whenever you have a good bracket, this is, now we call it a good bracket. Even is a good bracket. The problem is with odd and even. Now we'll talk about that in a minute.
Odd even is always not accessible, right?
Say it again?
So when f is odd and g is even, the system is always not accessible. Is that right?
No, it's actually accessible. We don't come to this point because the lark is satisfied. We don't come to this point unless the lark is satisfied. If the lark is not satisfied, I don't care about the type of the bracket. If the lark is not satisfied, I didn't cover the tension space, I'm not even accessible. But if I am accessible, I care about whether I am controllable or not, because accessibility is not a sufficient property that we aim for as control engineers. We need to go all the way around, okay? So we always care about controllability. The lark ensures accessibility, and from there we need to get something more to get controllability. If you are covering the tangent space, the lark, by all good brackets, then that's okay. If some of them are bad brackets, we'll see in a minute what can be done. So let's here talk in a little bit detail about controllability of this system, our control affine system. plus summation J GG UG from X0. Typically, X0 is an equilibrium point. And we can do that by linearization, actually. What do you mean by linearization? Introduce a small perturbation delta x. So by definition, here is a definition, is just x minus your equilibrium. And we assume that delta x is small, so we retain the only linear dynamics. So this is a times x, times delta x, I'm sorry, plus b times u, where a is the Jacobian of your dynamics at x0, so just bunch numbers, right? And b is bunch of vectors b1 up to bm, where each b is just your g evaluated at x0. Okay? So let's call this system star, and we have a condition for the controllability of a star. So if the rank of your B, AB, all these guys is n, what do we conclude about the controllability of a star? This is actually a necessary and sufficient condition for the controllability of a star. So a star is controllable, right? And if the linearized version is controllable, like any other property, stability or whatever, this is sufficient. If the linearized version is controllable, then the nonlinear version, sigma, is STLC, is small time locally controllable from x0. So this is a sufficient condition. But it's not necessary, we don't have this thing. We don't have it the other way around, so it's only sufficient. Okay? Any question about that? One thing here that I want you to remember, these B's are just what? Are the evaluation of GJ. So actually these are the G's, right? What's AB in the linear term? We just talked about that in a minute. What's this in our language of Lie bracket? This was the Lie bracket of F and G, right? And this is the Lie bracket of add F n minus 1 G. So these are actually Lie brackets. What you do in linear control, they are actually Lie brackets. So let's do the nonlinear controllability.